So I'm James Radomski. I'm one of the FORCAST Instrument scientists, along with Nicole Carneth and Wangi Lim, and we'll be helping you while you propose and observe with FORCAST. FORCAST is an imaging spectroscopy instrument that runs basically from 5 to 40 microns, so basically mid-infrared to the very beginnings of the far infrared. So there's some videos from last year that have more detailed examples, but I'm going to go over some tips and tricks and stuff to help you during your proposal. And when you're first in an initial plan, first thing to check, obviously, is check if the source is already observed in the archives. I mean, if it's already there and at the wavelengths you want, then basically you're done. Just download it and continue on with your publication. If it's not, it may be it may not be exactly your wavelengths, in which case, by all means, feel free to apply for different wavelengths that hasn't been looked at, because that will be absolutely new science. So you can search the archives. Everything's in URSA. There's the link. A tip is early cycle observations. First couple cycles SOFIA, we of course were commissioning, doing a lot of issues. So those observations may have very poor world coordinate system coordinates. So in that case, you might want to increase your, start off with a very large radius of say 600 arc seconds, and then slowly decrease it in case you have too many targets to look at to make sure your source is in the archive. The second thing, of course, and I'll show some live examples in a moment, is to check the feasibility observations. Before you start writing your science case, make sure it's even possible to do with FORCAST and SOFIA. Site, of course, which is mentioned before, is a good site to estimate signal and noise. Also, though, I'll show you later in the handbook, the cycle 9 and stuff, you also have a table of FORCAST sensitivities, which is a good double check and sanity check for your calculations. So one tip is if you're using flex estimates from previous observations for your source from WISE or Spitzer, MSX, Akari, whatever, you're probably fine using that. However, people still use IRAS flux points, which was an instrument launched in the 80s and stuff. IRAS, of course, had an enormous beam at that time, and so you're almost certainly overestimating the flux. So having observed in the early days from ground-based to IRAS observations, I noticed as kind of a tip, make sure if you have only IRAS observations, you divide that flux by 3 before you do your estimations. Because IRAS is almost always going to overestimate your flux. So pick a kind of a worst case scenario. The next thing, of course, another thing that tends to trip up a lot of people, including myself sometimes when I'm proposing, is make sure you download the latest USpot tool. We do change this quite a bit and stuff, and there's usually minor changes like that, but sometimes you get errors if you don't have the very latest one. So of course, if you proposed before and stuff, used it before, just double check, make sure and get the newest one before you start your proposal again. The next tip, we have a nice filter array of filters for FORCAST, which is in the handbook you can check. Double check to make sure your filters wanted are available. We have this link showing the filters. The ones in bold are usually the ones that are typically in there. So, and of note, some shorter wavelengths are not always available. For example, the 5.4 may not be available because we have the 5.6 micron and stuff. Although, feel free to ask ahead of time. We can also go by proposal pressure. If suddenly a lot of people want to use a certain filter, we could put it in and such. So just something to check when you're first planning out your proposal. Also, another note is some filters like the N prime 11.2 micron filter has some issues when it's used the dichroic mode and such. It's fine in single channel mode, but it does have some issues. So double check, like I said, the handbook for filters availability and any issues they may have. So let's see. Next slide. Okay. One thing, of course, is you should be thinking about your proposal as early as possible. Certainly, if you're going to ask questions or figure out what you want to do, sending questions to the help desk is very useful. Just in early planning, before you start planning out the specific proposal science and start writing it down, you just start getting an idea. Feel free to email the help desk early, because I'm an astronomer and I know all the astronomers, and all the proposals come in like at the last minute. So if suddenly you have some specific issues with FORCAST going, what's the sensitivity here, or what mode should I use, whatever, and it's an hour before the deadline, you're probably not going to get help. So, but when you're first planning stuff, before you even write proposal, like I said, download USpot, start putting in observations, select a target, stuff like that. The first thing you want to look into is what mode you want to choose. So NMC, non-match chop, is a compact source, is a typical mid-IR. You just chop on just off the source and such. That's our most efficient mode. C2 and C2 is our asymmetric mode, which is for very extended sources where you need to chop off to avoid contamination. So if you're looking at very extended regions like that, you want to choose asymmetric mode because it's not quite as efficient. There's more overheads and stuff because you got to move the telescope much farther away and such. But it does avoid all contamination of chopping onto stuff in these large regions. So one tip, and I'll show you that in a live demonstration, is when you're first setting up your observation, you're checking off source, it's good to use maybe the MSX images in U-spot. Try to pick the closest wavelengths. If you're doing 8 microns, use the 8 micron. If you're doing 20, use the 22. If you're using 37, use the longest one that's available, like 22 microns and such. MSX is probably the best. WISE is also useful. If you have your own Spitzer data, just a note to be careful, because Spitzer is not ideal, because Spitzer was a space-based mission and was super sensitive. In fact, like I said, a lot of targets we look at, as mentioned before, have been completely saturated by Spitzer. So you may get a confused region if you're trying to chop off source there. If you look at your Spitzer image, there's just emission everywhere. Well, if you look at MSX, you'll see that, well, actually, there are some clean regions that FORCAST won't see anything. So if you're looking at some relatively bright targets, you'll be fine. So for spectroscopy, we just call the C2 and C2 mode there, the asymmetric, just NXCAC. So they have basically the same modes as the imaging and stuff. So you can use non-matched chops, typical, or you can use this NXCAC if you want to get your spectron a very extended source and make sure you chop and not off the source. Now, one note, important for FORCAST spectroscopy is you don't have an instrument rotator. So you can't necessarily choose the angle of the slit, which can be important if you're looking at some very elongated target. You want to put a slit right along that elongation, is we can't guarantee that at the time we observe, the rotation on the sky will line up the slit so it's right along that elongation. So that can be tricky. There are a couple ways around that. It usually just means asking for more time. One is just to, like I said, it is possible sometimes that we can kind of plan it during the part of the night where the rotation angle is right on the source, but that's very tough to do, so I wouldn't recommend that. If you really need some spectroscopy along like an extended region, whatever, you want it all along the slit, a couple ways around it is to choose slit scan mode to try to scan across the region, or just put a couple extra slits down there. For example, if you put like 3 different slits, one in the middle, one on either side, you can kind of get at least samples across the whole, source, regardless of the position angle on sky at the time. So, and like I said, if you have difficulties planning this, feel free to email the help desk and we can help you through that. Now, another note, as was mentioned previous, SOFIA is an actual plane, which means we need to return home. So, for example, if you're working from the ground, you can plan a 10-hour observations on a long night. We have to turn around and come back, so we can only observe one part of the sky for most, maybe 4 hours and stuff, with typical observing legs around 2 hours. So just keep that in mind when you're planning your observation, that you're going to have to split it up and chop it up in a way that makes sense so you can add it back together later and stuff. So let's see now. Now I'll show you some live demonstration of some of the things I talked about. So, and as I mentioned before, I only have so much time, like 20 minutes like that. So my previous collaborator, Ralph Schuping, last year did some really nice YouTube videos in detail going over the same kind of stuff. So feel free to check that for both imaging and spectroscopy if you want to see a little more in detail. So now let me just set my full screen. So, okay. So let's go into a typical observation. So this is a, here's U-spot. So just double check, you can see U-spot, right, Cassandra? Excellent. Okay, so this is one of our legacy programs from cycle 7, the Galactic Center, which turned out very well. We did a full mosaic of like 33 fields or something across the entire Galactic Center, covering 25 and 37 microns, much of which was the shorter wavelengths, 25 microns, was completely saturated in MIPS and stuff. So it was a very nice data set. So, but here's an example. Here's one of the fields and stuff. So here's Here's the galactic center, as you can see in DS9. And you can see all the different fields we observed right across here. So, and one note, notice that we observed this over several nights, over a week and stuff. But targets right here, you can see was observed on the same night, but it was rotating relatively fast in the sky. So we did this one region, and then right after it, we followed this other region. You can see there's a bit of rotation of the field of view, and same here. So things aren't all lined up in the same way, so they rotate over time. So you could see in this case right here, the two squares, this could rotate at a bang angle where maybe you don't get enough overlap here. So that's good to check rotation. I'll show you how to do that in USpot. So here is an example of one of the fields. I think this is over here in Sag B and such now. Now here we look at the MIPS Spitzer, which I was talking about. So here's the field that's on the source right there. That's one of the fields right here. Now this is asymmetric mode. So this is chopping and nodding way off the source of 400 arc seconds like that. So it goes over here and then it nods and then chops over here. And as you can see, looking at Spitzer, MIPS 24 microns. One of the reasons you can also see why we observe at FORCAST, it's completely saturated in only important regions like that. But if you just looked at Spitzer, you go, oh no, look, we've got all this emission right in here. There's some stars right here. Look at all these stars. We're going to chop onto this. This is going to contaminate our emission. But if you look at the MSX field, which is the same field, you say, oh wait, actually, this is actually pretty clean. So based on the sensitivities, MSX is a little closer to FORCAST. You can go, well, actually, these are relatively clean areas. We'll be fine. And we were fine for most of these sources. Every once in a while, you may pick up a faint source that you don't necessarily see. But it's a good recommendation. Too many people start off and always use C2 and C2 mode, which is not very efficient because they're using Spitzer data. And they're like, oh, I got to get way off this emission to see anything. Where something like MSX or even WISE helps you a little better understand. So, and just to show you what the observations looks like, here we go. Here's the AOR, exposure time. This is dual imaging, which is our most popular mode. 25 micron, 37 micron, so we can do image at the short wavelength camera and the long wavelength camera. So there's the mode, the chop throw, chop angle, nod throw, and stuff right here. And here's the example rotation angle, which is very good, because this is what you can see how much it twists on sky. So right here, it's set to 240 and stuff. But if I set this to like 0 and apply, oh yeah, that's right, it's something to say. But anyway, you can change that angle, and you can see this basically the square spin around. So you can double check to make sure if you're doing a mosaic and overlaps properly and such. So, and that's just done with the with this example rotation angle. So you can just play around with that and stuff and just see how the target spins depending on what time of the night we observe it and stuff. You can choose your dither pattern here. One thing to note, of course, is we're not like the near infrared, so we don't have to have like a whole bunch of dithers. In fact, we usually don't dither a lot. This is a rare program where we had a lot of dithers. Typically, 3 dithers is more than enough to take out any of the bad pixels like that. And of course, if we're doing very faint objects over several nights, we may just choose not to dither and just over several nights use that as kind of a dither because we never quite come to the exact same position, the exact same pixel. So that kind of works there. So don't, well, that's one thing that happens. Some people go crazy on the dither pattern and such. So, and of course, you can change the mode here, the non-matched chop. Mind you, they have different limitations. C2 and C2 goes much longer out there. Non-matched chop, you don't want to chop throw longer than maybe 120 arc seconds, like that. After that, because it's symmetric, it starts getting distorted a little bit. So if you check the handbook, all the details as far as the limits in each mode and stuff are there. So, and of course, if you have any comments, there's a comment field to put comments. So just to show you some of an example of our highlights, this is the galactic center image from SOFIA. This is a combination of the 25, 37 micron, along with Spitzer 8 micron and Herschel's 70 micron data of the galactic center. You see it covers quite a bit. So we can do some impressive mosaics. And it's relatively new that not only do we do mosaics, but now we have a level 4 processing for FORCAST where we can combine the mosaics for you. It takes a little longer and stuff because it's a little tricky, and I'll go over those details in a moment. But if you are planning a mosaic of a very large region of sky, like a massive star forming region, feel free to email early and we can help you plan this out and we come up with some very nice data set. Here's the galactic center, which is legacy data freely available for you to download, start doing science on right now if you want. Another of our greatest hits is the M17 region right here, which of course was only like maybe, I think, 10 fields, 10 or 11 fields. So this is maybe 3 fields across. It wasn't the monster that this was, but still, it came out quite nice. So now I mentioned, like I said, one of the things you check while you're planning that new spot is to check the signal and noise. Now, site for forecast is pretty simple. Here's the numbers right here. You know, you can basically put it in. The Grism calculator is right here. One thing I'd recommend right off is do a sanity check and check the handbook, because the handbook forecast is a cycle 9. The handbook is there's a link right to it and stuff like that. Forecast. So what this nice has is not only it shows you the filters that are available right here, the ones in bold. Like example, we don't normally have the 5.4, but we do have the 5.6 in there and the 6.4, but not necessarily the 6.6. So it shows you the filters available and their profiles. But it also has a nice sensitivity table right here, which is a good sanity check. So this is all stated above. So basically, let's give an example for an 11 micron filter in single channel mode. To get a signal noise of 900 seconds, you can look at a 79 millijansky point source. So if you put that in here,
minutes.
what? Sorry.
Sorry, you have about 5 minutes.
Okay, I thought I had till 9:20.
Yes, we would like to have some time for questions.
Okay, all right. Well, I'm almost done. So where was it? So right here, this is a good example. Like I said, you can put these numbers in here. Site. So here's single channel. There's no double channel. 900 seconds. Signal noise of 4. 79.4 millijanskys, which is 0.079 janskys. You put in a typical. You calculate it, and there you go. Signal noise of 4, 900 seconds, just as a table. So you can use this table to double check for both imaging and the Grism calculator and stuff, because we also have in the filter list some Grism sensitivities. I think they're down here. Here you go. So you can check these too, just to make sure you're doing everything correct. One thing to note as far as single double channel mode, double channel is very popular. You can see, for example, like 11 microns, there's not much change. In fact, this is kind of misleading because it looks like it gets better with the dichroic in there, but actually this is within the error of 10 to 15%. So, but for example, if you want to use double filters and you want to use the 5.4 micron or 5.6, you see the increase of flux you see to get the same signal noise is enormous. So you'll get killed here at these short wavelengths. So in this case, you might want to just take a separate single filter image at 5.6 microns and stuff. You also take more hits at the longer wavelengths. So in case something's very faint at longer wavelengths and you really want to get that, you might want to go to a single filter and just hammer on it there and such. So, and some people use a combination of single and double filters just to cover it all and such. And like I said, the Grism calculator is the same way. You can calculate signal and noise. This was already put in before. And you can see this is signal and noise from the table at 11.1 microns of about 4, signal noise of 4 in about 900 seconds on a point source, 449 millijanskys. And you see that's about average, but you see it does change by wavelength in this filter. So we get hammered. We still got the ozone feature even in the stratosphere and stuff. So that's good to plot. You also, a nice plot is you can check instead of signal noise, you can also check limiting flux. So if you submit that, see, you get a nice table and it shows you the limiting flux by wavelengths. Actually, you can see it needs something in the ozone feature very bright in order to detect anything and such. So this is useful. One thing to note for spectroscopy is you want to, for imaging, of course, you can go for signal noise of 5 to 10 and stuff, which is on the low side. For spectroscopy, you want to aim for a signal noise of around 50 and such. So, I mean, if you get around 40 and stuff, in order to actually take out the telluric correction pretty well, it's like that. I mean, if you're getting a signal noise of only like 5 or 6 in spectroscopy, you're going to have problems. So you want to aim for a higher signal noise to get good data there. So, all right, now going back to PowerPoint. Go. Just some final points. Once again, if you're doing a forecast mosaic, currently we don't have a mapping mode. So as you saw in that US spot proposal, we had a observation for each position along that map. Make sure you account for a rotation of field, as I mentioned. One thing is forecast has some slight distortion at the edges of maybe a few pixels. So sometimes exact alignment can be a little tricky. So keep that in note, though we can work around that at some level. And once again, we do like I said, if you plan this out, we do help you stitch together and offer you a product of the fully stitched together mosaic and stuff, which is very nice. So, and if you have any questions, as I mentioned before, contact the help desk. The earlier the better. Like I said, it's best to do your feasibility and just initial checks as early as possible to make sure things make sense. And if you have questions, email us early. So, and then you can work on the nuts and bolts later and submit it last minute like we all do. So, thank you very much, and I'll take questions. Let me unshare this somehow.
Hey, James. This is Ariel. I have a question from Ryan. So he read on the call for proposal that the instrument offered for the southern deployment are great hot-cross PTLS. So does this mean that southern hemisphere targets will be inaccessible with FORCAST in Cycle 9?
I'm sorry, I didn't hear that. What was that again? That the
So there is no planned southern deployment with FORCAST. So
no,
does this
at this
mean
time there is
southern
no plan
hemisphere
for
targets?
Yeah.
So what about southern hemisphere targets with FORCAST in Cycle 9? They're not accessible. How
Yeah,
far
right now,
south can you?
yeah, right now we don't have. I think it's in a proposal that there's no planned um, southern deployment for FORCAST. So as far as checking how far south you can go, you can use Palmdale as a rough estimate. You know, you can check. There's a lot of visibility tools online and stuff just to check. So we can go a little south from Palmdale and stuff over the Pacific and such. So, but that gives you a rough estimate and stuff of what we can observe. So stuff really south, not so much. We can get basically slightly south though. Like
You can get to the Galactic Center, but
yeah, we
probably
can
not
get to
much
Galactic
further
Center.
south.
So, but that's still
Minus 27.
yeah. So minus 27, minus 30.
Hey, James.
Yeah.
You may want to mention that we also have our own visibility tool on DCS website.
Yes, it's also there's some visibility on, like I said, there's several tools on our website. I think USpot has some visibility tools built in too and such. So feel free to check those. All right. Thank you very much.
Thanks, James.